The next example asks for what values of p is the series 1 over n to the p power convergent. We can again use our integral test for this and say the integral of 1 over x to the p power dx from 1 to infinity. And then we can integrate this using the different cases. So as long as, well, I guess we could start with case 1, p equals 1. If p equals 1, what happens? Then we have 1 over x, and the integral becomes the ln of x, of course with the absolute value. Actually the limit as t approaches infinity from 1 to t. What happens to this integral? Well, I'm just going to jump to the answer. It is infinite because the ln of a very large number is very large. That is an infinite limit. So we have an infinite integral, which means when p equals 1, then this is divergent. Okay, what if p is not 1? If p is not 1, I don't know why I wrote this again. Case 2, p is not equal to 1. Then we have the limit as t approaches infinity of, this is now the power rule, x to the p negative p plus 1 divided by negative p plus 1 from 1 to t. So what seems like we've done this problem before. What kind of values for p will make this limit a number and not divergent? Well, if p is greater than 1, what happens? If p is greater than 1, then the power up here is a negative number, which brings this fraction to the denominator, which brings the x to the denominator, and then as t, as x, approaches infinity, that part of the limit goes to 0, and everything's good. So if p is greater than 1, we have a convergent integral. If p is less than 1, if p is less than 1, then you have 1 minus something less than 1 is going to be greater than 0. X to the greater than 0 power, now the x stays in the numerator, and if the thing in the numerator approaches infinity, this fraction is now going to infinity, and then we have a divergent series. This happens, this type of problem shows up a bit, and it's got a name. It is called a p-series. Okay, so one example of a p-series is the harmonic series. We saw this one before, and we looked at the partial sums to show that it was divergent. But now you can use the fact that it's a p-series with p equals 1. So integral test about system element series. This is a p-series with p equals 1. So it's just case 1 that we saw above. So it is divergent. Next example, we are looking at the sum of the ln of n divided by n. And we want to determine whether or not it converges or diverges. So I suppose we should mention whether or not it's positive, continuous, and decreasing. If n is 1, then we have the ln of 1 is 0 over n. If ln is 2, we get a positive number over positive number. So that starts out at 0, then it goes up to a positive number. So is this actually a decreasing function? Well, it is decreasing in the tail. So as long as we're on the right-hand side of this, it is a decreasing function. So from not from 1 to 2, but when n is greater than 1, that is from 2 on, this is a decreasing function. So if we've got the integral from 1 to infinity, or if you want, you could we could go from 2 to infinity if you're not convinced that using 1's okay. The ln of x divided by x dx. You know, this is a u substitution problem where we can do the substitution in our head. U equals the ln of t, so du equals 1 over x dx. So this integral becomes the limit as t approaches infinity of, so this is my u du, looks like the ln of x squared from 2 to infinity. Not much else to do here. We know that as if x is approaching infinity, ln of infinity is very large. Squared, it's still very large. So this is going to infinity. And that means this is a divergent. So the sum is divergent as well. And there you have it. That is the integral test.